probably seen a scene like this in a movie. A speeding car or truck's about to hit someone. The person dives out of the way to avoid being hit. Or while watching football, a defensive back tries to chase down a ball carrier from across the field. Or in soccer, a goalie dives to save a penalty kick. Each of these situations has something in common. A person has to choose an angle or direction before pursuing or escaping. If I was in the way of the truck, my instinct would be to jump directly to the curb. But maybe my instinct is wrong. Maybe I should jump away from the vehicle a little. Or maybe a lot. And what about the defensive back? What angle should he take to catch the ball carrier? Does the angle depend on the defensive back's speed or the speed of the ball carrier? In soccer, I see a lot of goalkeepers jump down the goal line to try to stop the soccer ball. But is that the best option? Maybe they should try to intercept it before it gets too far away from them, diving for the closest point on the path the ball is taking. Let's take each of these situations, math them out, and see what we learn. Before we dive in, it's helpful to know that all these situations can be thought of as the same problem mathematically. We can relate the goalkeeper and the defensive back problems to the truck problem. We can think of the ball carrier or soccer ball as the corner of the truck barreling toward or by the defensive back and goalie. There are, of course, a few differences, but we'll discuss those more in other videos dedicated to those situations. In this video, what we're going to do is we're going to solve the truck evasion problem using only junior high mathematics. But we have two other videos that use a pre-calculus solution and a calculus solution that are linked in the description below. We also explore the goalkeeper and football situations in separate videos, and they're linked below as well. Here's a diagram of the truck evasion situation. Let's call the person in the street Sarah, after my only daughter. Sarah's walking towards the curb when she notices a large truck coming towards her. Let's make some reasonable assumptions about distances. Let's say the part of Sarah furthest from the curb is 10 feet away from the curb, and the truck's 40 feet away from Sarah. To first analyze this problem, let's think about the question, what point on the curb should Sarah run to? We'll come back to what angle she takes later in the video, but if we focus on what point on the curb she runs to, we can use junior high mathematics. The shortest path for Sarah to get to the curb is this perpendicular path. But we're not trying to minimize the time it takes her to get to the curb. We're trying to maximize the time between Sarah getting to the curb and the truck getting to Sarah. Running towards the truck is obviously not a good choice. That increases her distance to the curb and decreases the truck's distance to her. So that'll be worse for Sarah. But perhaps running away from the truck a little might be safer for Sarah. Suppose instead of running perpendicular to the curb, she ran to a point 1 foot down the curb from perpendicular. This increases the truck's distance to Sarah, but also increases Sarah's distance to the curb. How much though? We can use the Pythagorean theorem to find out Sarah's distance. Her path is the hypotenuse of this right triangle with legs of length 10 and 1. So her new distance is the square root of 101, which is about 10.05 feet. Doing this forces the truck to move 1 foot more, and Sarah only has to move a small fraction of that, 0.05 feet more, or 1/20th of a foot. Well, what if Sarah aims for 2 feet down the curb instead of 1? This gives us a new right triangle with legs of 10 feet and 2 feet, and a hypotenuse of the square root of 104, which is about 10.2 feet. Notice that now Sarah has to run another 0.15 feet to get the truck to travel 1 more extra foot. Is this a better option for Sarah than running just 1 foot down the curb? Well, that all depends on the speeds of Sarah and the truck. Let's assume the truck is moving at 25 miles an hour. Let's say Sarah can move an average of speed of 8 miles an hour while she sprints to the curb. We'll convert these speeds from miles an hour to feet per second to match the units, which is feet, of our situation. This gives us speeds of 11.7 feet per second for Sarah and 36.7 feet per second for the truck. With assumptions about speeds, we can calculate how much time Sarah actually gains getting to the curb. Since rate times time equals distance, then the time equals distance divided by the rate. If Sarah goes directly to the curb, it'll take her about 0.85 seconds to get there. If Sarah aims for 1 foot down the curb, the truck goes 1 more foot, Sarah goes about 0.05 more feet. That's an additional 0.027 seconds for the truck, and for Sarah, a minuscule 0.0043 seconds. So Sarah gets about 0.023 seconds more to get to the curb before the truck gets to her. If Sarah goes 2 feet down the curb, then the truck has to take another 0.027 seconds, but Sarah has to travel an additional 0.15 feet, and that takes her about 0.013 seconds. So Sarah saves an additional 0.14 seconds. Going 1 foot gives Sarah an extra 0.023 seconds. Going another foot down the curb gives her another 0.014 seconds. That is a total of about 0.037 seconds extra for Sarah to get to the curb. We could keep going 3, 4, 5 feet down the curb until we find Sarah starts losing time instead of gaining time, but that might take a while. Using a spreadsheet can save us time making these calculations. From the spreadsheet, we find that the optimal place for Sarah to run to is somewhere between 3 and 4 feet down the curb. We'll estimate the optimal spot to be 3.5 feet. This is great. We now have enough information to save my daughter. And for this situation, this level of accuracy is good enough, because in reality, Sarah would be lucky if she could guess even within a foot of the optimal spot in such an intense moment. It might be easier though for Sarah to estimate an angle to take instead of a point on the curb, and the angle would be the same no matter how far away she is from the curb. The solution of 3.5 only works if she's exactly 10 feet away from the curb. A simple way to find the approximate optimal angle that Sarah takes is to use the measurements 10 and 35 in the problem to draw a right triangle with legs 10 units and 3.5 units. Now we can use a protractor to measure the angle. It's about 20 degrees, maybe a touch less. We could also use dynamic geometry software such as Algebra and get a similar result. Now, if all we cared about was this particular angle to this accuracy, we could stop here. However, there are other ways to solve this problem where we create a mathematical model that can be easily analyzed and transferred to other situations, like the football and soccer situations. And that'll help us answer additional questions like, does the angle depend on how far away the truck is? How does the angle change if the speeds of Sarah or the truck change? Is it safer for Sarah to err on one side of the optimal angle or the other? We'll answer these questions and more in part 3 of the video series. Thank you so much for watching. Please subscribe and share our videos. The description also includes references to an article where I first bumped into the truck evasion problem, as well as a follow-up article that builds on this math and shows that the path of the planets of our solar system are like astronomical pedestrians continually doing the kind of math we're doing to always avoid being hit by the oncoming sun.